So if you've been following this column for a while, you'll know that I have a bit of a thing for things that glow, whether it be luminol, luminol again, or singlet oxygen chemiluminescence. But I've never actually got around to doing an actual glow stick reaction. So here we are. So this reaction is based on one that was developed by Roger Nixon as part of a workshop that he did out of Oxford University when he was school teacher fellow there, based around sort of 2010, 2011. And you can go and read the original article he wrote up in School Science Review. But the thing was about the original setup was that they were going out and using some fairly expensive dyes and some solvents that weren't necessarily appropriate for use in a school, such as dichloromethane. And so I wanted to see whether or not it was possible to sort of get this glow stick reaction at a reasonable price point and get an approximation of something that was going to be satisfactory to students and potentially initiate some ideas for some research for them to go on work on with in the future. So these commercial glow stick systems tend to be based around the chemistry of oxalate esters, and the one we're going to be using today is TCPO, trichlorophenol oxalate. Now it's going to be much easier and cheaper for you to be able to make this in school than it would be for you to buy it on its own, and that's a synthesis that's simple enough that even a sixth former or an IB student could do actually under fairly close supervision. And you'll get a fairly decent yield out of a respectable amount of starting material. And once you've got that, this stuff will be fairly shelf stable for a number of months, and that's what makes this one particularly suitable for a starting point for these kinds of investigations. I also have some solvents, and we'll see the effects of the solvent shortly. For today we're going to be using a 50-50 mixture of ethyl acetate and ethanol, and I've got those separately here, 5 ml of each, just to illustrate why we want both in the mix there. I've also got some sodium acetate, and that's going to catalyze the reaction for us, and 2 centimeter cubed of 10-vol hydrogen peroxide made up in ethanol rather than being made up in water. So all we need to do to initiate the reaction is a sample vial and basically half a spatula of the TCPO. It's about 0.1 grams. Okay, and once you've got that, you will add in order. I'm going to go in with this to begin with. This is the ethyl acetate. Now if I add in the dye to the ethyl acetate, you'll notice I've got about, by the way, this tip of a splint here. It's about 0.05 grams of the dye, and you can see here that it's not really dissolving in the ethyl acetate on its own. The dye that I'm using here to accept the energy from this chemiluminescent reaction is rhodamine B, also known as rhodamine 610. It's a laser dye, and there are loads of different fluorescent dyes that will actually facilitate this reaction and get a glow for you. This one's going to glow kind of a pinky red color. The other dyes tend to be a little bit better, if I'm honest, but a lot more expensive. So to start off with, rhodamine B is a good place to go. But you can see here the ethyl acetate that we want to actually dissolve our TCPO up into. The rhodamine B, not so interested in that. A little bit of ethanol here, and immediately you can see that the dye is doing its business. Just to get this ready, as I said, the end of a splint of catalytic sodium acetate, and because I'm going to be working in fairly dim conditions, I have my peroxide already measured up in a syringe for me, so it's nice and easy for me to work with. I'll clear the other stuff out of the way and we'll have a look and see what the reaction looks like. Okay, so I've dimmed the lights, and as I mentioned, what we're looking out for here is the idea that we've got this sort of chemiluminescent reaction. There is going to be some catalytic behavior from our sodium acetate dye, and so we might notice that actually more of the glow is taking place around the dye itself. First of all, I'm going to just put in the peroxide relatively slowly so we don't mix the liquid up too much. Okay, and you can see we've got some glow taking place up at the top, and if we mix this through so that the sodium acetate and the various components are thoroughly mixed, we get a nice glow there coming from the peroxide and the reaction. Now, what's good about this demonstration is that it can be used as a great launching point for any number of different investigations for science clubs or for students who are working on individual projects. First of all, you've got the idea of the synthesis in the first place, things that affect the yield, the rate of that reaction, the thing that you're actually synthesizing as well. This is not the only oxalate ester that actually has a chemiluminescent reaction. The one that was chosen today was taken for its balance of shelf life and the strength of the glow associated with it, but other ones are available. You can even look at green alternatives using vanillin rather than the trichlorophenol as an alternative. Of course, other fluorescent dyes are available, and you can look at the effects of those, as well as solvent effects. So there's a whole range of different things that can be tried out, and so definitely worth actually showing to students to see if they want to take it anywhere. Give it a go.